So in this video, I'm going to explain the chapter 2 of Verilog HDL. The basic unit of description of Verilog is a module. In this chapter, it describes how Verilog works in general. The structure of design is used using switch level primitives, gate level primitives, and user defined primitives. Um, so this is the basic syntax of a module. First we will start with module, that key term, and then a module name, port list, and then we will use declarations, what the port list are, and then the statements. The statements can be of either gate level, switch level, behavioral level, or data flow level. And after that we can use the end module key term to end the module. So let's take example for half adder, and as we know, in half adder, sum is the uh, XOR operation of the input, and carry is the AND operation of the input, if I'm not wrong. Yeah, so this is the module for half adder. So you can see that we started the module with the module key term, then we used a primitive name which is half adder by ourselves, and then we have mentioned the port A, B, sum and carry. Then we specified that which are the inputs and which are the outputs. After that we assign some kind of delays using assign #2. #2 defines the 2 units of delay. Then we say sum is equal to A and B, I mean A XOR B, and its carry is A and B. And then after that we use end module, and this is a basic example of a half adder circuit. Now moving on, here all the ports are of size 1 bit since no range has been specified. This is an important point. And the 4 ports here are net data type. So within a module, a design can be described as the following styles: data flow style, behavioral style, structural style, and any mix of the above, like data flow, behavioral, and structure. We will talk about it as we move ahead. Um, let's talk about delays. All delays in variable HTL module are specified in terms of time units. Uh, Assigned to hashtag reference after 2 nanoseconds of delays, this part will be executed. And then sum will be A XOR B after 2 nanoseconds from the current simulation time. Okay. Then here time scale, 1 nanosecond by 100 picosecond. It determines that how the time unit is treated, like how it is a unit of time is treated in the circuit. Okay. So here it says that the time unit is treated as 1 nanosecond, and the time precision is to be 100 picosecond. So here it will be 2 nanosecond per if hashtag 2 is 2 nanosecond per 100 picoseconds. This is how the time delay is going to work. Now if you don't describe any time scale, the Verilog the simulator may default to be a certain time unit. Default time unit will be unspecified by the IEEE standards. Now let's talk about different side of declaring. Okay. Describing in data flow style. The basic mechanism used to model a design in the data flow style is the continuous assignment. And in a continuous assignment, a value is assigned to a net. So the net data type is used. If data types are of uh, two type probably, you can net or raster type. So data flow level is used to for continuous assignment, and always net uh, data type is being used. So how we write the how to write the syntax? We first use the assign keyword, the delay, and then the I mean net variable along with the right hand side expression. So if no delay specified, by default it's zero delay. So let's take an example of a 2 to 4 decoder. So, so first we specify the time scale, then 1 nanosecond per nanosecond. So every nanosecond describes is considered to be 1 nanosecond. Then the module name we use is decoder 24. So yeah. We have performed a lot of NOT operations in this. So we assigned a bar, b bar to NOT of a and NOT of b. The first statement, the one is a backcode, the example of a compile directive. The compile directive timescale. Yeah. A bar and b bar are a wire type, and we have described it in the declaration part. So here, according to the delays, the statements are executed, and it is and here is a timing diagram of when and which execution happens. You can see, and here it's continuous statements. So every assignment will happen after the other. So based on that, just a second, I clicked somewhere else. Yeah. Second, this delay assignment works since it's a continuous assignment, so all the blocks will run together, and delay according to the delays, these are the ways. Now let's talk about the behavior level. In behavior level, it's an initial statement, and there is the always statement. Only a registered data type can be assigned to a value in either of the statement. So remember that in behavioral type of modeling, a registered data type is used. So here is an example of a full adder. Yeah. So here the ports are A, B, C in, sum and C out. The inputs are A and B. The output are sum and C out. We have assigned two registered data types, sum and count, C out, and three other registered data types, T1, T2, and T3. Okay. Then we have used an always block. An always block, it starts with an and at the rate operator. In case it's A or B or C, that's a condition, and we begin it. So here you can see the syntax, and according to this, the program is executed. Delays are now specified into types: inter-statement delay and intra-statement delay. In intra-statement delay, the delay is this is the delay by which a statement's execution is delayed. Inter-statement delay, this is the delay between computing the value of right hand side expression and the assignment to the left hand side. Excuse me. So some of the examples of inter-statement delay. Sum is A XOR B XOR C in. Hashtag 4 is after the first sig. So after the first sequence, Interstatement delay, this is the delay by which a statement execution is delayed. So the second line of hashtag 4. So after 4 unit of time, the T1 equal to A and C in this operation will be performed. For interstatement delay, sum is equal to hash 3. Then the delay between computing the value of the right hand side expression and assignment to the left hand side. So yeah, so this is the delay. The A and B and C operations are done, and after 3 units of time it is assigned to sum. This is example of initial statement. So initial block we use, and then we use begin and end. Describe now the structure type. Structures can be described in Verilog using built-in gate primitives, switch level primitives, user defined primitives, and model instances. So built-in gate primitives examples are like AND gate or gate XOR gates. Switch level primitives we use CMOS, PMOS, and MOS to describe positive terminal or negative terminal, and it is very hard to code. We mostly uses user defined primitives, the last as we saw in full adder and half adder circuit. It is easier to write codes and understand. Lastly, we have module instances. This is a 4-bit full adder examples. Let's talk about simulating a design. So we talked about mixed design style initially. So when a module structural behavior constructs can be mixed freely. This module can contain a mixture of gate instantiation. So here XOR operation is being used. Always statement is continuous statement used. So three instantiation, three level of abstractions are used at one point of time. This is an example for mixed design style. Now with this I would like to conclude the second chapter, and then move to the third chapter in the next video.